Hi everyone. After taking data for the day 2 analysis on the simple harmonic motion lab where we investigated period versus mass, we likely would have had a classroom discussion about that relationship to see if we could learn anything and whether we could come up with an expression that might be useful in describing the system. So in a semi-brief video, I'm going to sort of go through the discussion that we likely would have had in class. Everybody knows roughly what we did. We used this this applet to collect data in which we can adjust all 4 of these things. You might have the question, like, would we have done this lab in class? The answer is yes. We would have gotten out a spring of some spring constant. We wouldn't have changed the gravitational field because we all would have been on the same planet. And then we would have set some value of amplitude and then changed our independent variable of mass. And that's what you guys did with this applet. So collect some data, look down here, build a position versus time graph, find the period either from crest to crest or trough to trough, take that data, fill in a data table, choose a different value of the independent variable, collect data, see how that produces a graph. What's that period? And then we asked you to graph that. And you use this graphing program to show the relationship between those 2 variables. It has a nice curve fit feature. You're able to pick the relationship. Only a few of these seem like they might be going the right direction. A linear model seems like it fits most of the data. We have a couple problems here, though. One of them is that the data seems to curve, whereas the model is straight. It's okay for maybe data in between here and here. We could predict the period a little bit for those. But if we just kept collecting data, it almost seems like the data would continue going this way, whereas the linear model would continue going this way. So I also have a problem with this intercept here. I can't really explain why a mass of 0 grams on the end of the spring would produce a period of 0.3. I would expect no mass to mean it's going very quickly, and so as the mass approaches 0, I would expect the period to also approach 0. So I'm looking for something that might curve and also have that. A square root curve is a much better option here. And that's the mass to the 1/2 power, which kind of gives us that constant in front. But this is a math model. And here's sort of everything together. The experimental setup shown with the variables we used and the constants, our actual data table, and then the graphed data with the math model. In class, we might have used Vernier's LogRPro or graphical analysis. This is the exact same data. I've labeled the data series with the constant we selected, spring constant of 15 newtons per meter and an amplitude of 3 centimeters. But we would do the analysis very similar to the conversation we just had. We could choose any power here. And what do you know? To the 1/2 power. In order to make it exact, I might then choose variable power and make it exactly 0.5. Try fit, and there I have it. So increasing the font a bit for appearance, I get a math model that's almost exactly the same, where this is this constant here. A little bit unfortunate that for any power fit, LogRPro puts an A in here, which is perfectly fine. The problem is it also happens to be our amplitude, and these are in no way the same number. This is saying the constant in front of here is 0.514. You know, and either one of those methods would have allowed us to get what we were after, which is a mathematical relationship between the two. This is saying it the exact same thing, but just a little bit more condensed, that the period is equal to the square root of the mass, in grams in this case, times this number. Now, what could we do with that? Well, we could solve problems for that system. So If we were given a problem such as this, indicating the spring constant and the amplitude, would we be able to predict the period of the oscillation when the hanging mass is 400 grams? Well, we have a math model that allows us to do that. So if 400 grams, I plug that in for mass, take the square root of that, it's 20, multiply 20 by this constant out front, and I get 1.02 seconds. Question you may have, where did seconds come from? You know, do I just say, well, this is period in seconds and this is mass in grams, and then we just multiply it? In reality, no. If you're not into that analysis, then you might just want to close your eyes for the next minute. But I'll just show you kind of what really happens and then redo this problem with the correct units. So, bonus topic. To figure out the units of this thing, we actually consider the units of everything. But what I'm asking here is if mass goes in here and it's in grams, and period gets spit out here and it's in seconds, what do these units have to be? Because square root of mass gram or mass units is not seconds, and that means multiplying the square root of mass units by something has to give us time units. So what goes there? In order to visualize it, we will put in seconds as our units for period and grams as our units of mass. In reality, there'd be a number there, but we have to do the same thing to the units as we do to the numbers. So when a mass like 400 grams goes in here, this would be square root 400, but it's also square root grams. So whatever this is, it's going to come out as square root grams. And then we have to multiply it by these units and this number, yes, but these units to get the seconds. So it looks a little silly, but it kind of stands to reason that if we had something in units of seconds per square root grams, then when we multiplied it by square root grams, we would get seconds, and that's what we'd want. So these are actually the units of this constant out here. This is a more appropriate way to write it, with the seconds over square root grams being associated with this constant. I'll redo that problem just like that, plugging it in with the correct units associated with the constant, and then plugging it in with these. Like I said, it'd be square root 400 is 20, square root grams is square root grams. Multiplying square root grams by this unit gives me these this many seconds. So that's the exact right way to do it with units. We could do the opposite problem. Instead of this being the given and this being the unknown, what if this was the given and this is the unknown? What is the mass that would be required to produce an oscillating period of 0.8 seconds? I'm not going to do this one with the units. That was just to illustrate what we would just kind of maybe know what the units are, or it would be in the the problem introduction or something. But in this one, I put in a period of 0.8, and I'm going to solve for m, divide both sides by 0.051, square both sides to isolate the m, and our answer would be 246 grams. Now, we have a math model we could just really kind of see really quick. If I wanted a period of 0.8, it looks like I would need a mass of a little bit over 246 grams. So. Now the big question for us is, what if we had done this differently? What if we changed mass as our independent variable, but had a different set of constants here? We're not going to change this, like I said, but what if we did it with a different spring constant, different amplitude? Would this number change, and would this number change? Well, let's do it. Increase the spring constant. Looks like amplitude's too large, so I'll decrease this down to a centimeter. And then I can just cycle through the mass again. So run the same experiment, just with a different selection of constants. So collect, there it is. Get the period, put it in a data table, increase the value of the mass or the independent variable, collect. Seems like the same effect. As I increase mass, it did appear to slow down, right? Keep collecting, go all the way up. Take all 6 data points. I'm certainly seeing the trend of the data being that as I increase mass, again, the period takes longer. But do we get the same relationship? And here's the data right here. So do we get the same number? The answer is yes and no. The yes comes with this power. So even when I change these things, it still appears that the relationship between period and mass is to the square root power, to the square root of m. But this constant here changed. So it seems like changing these two things, spring constant, amplitude, changed this, but not this. Here's that data in Logger Pro with the data series named with the new constants, 25 newtons per meter, 1 centimeter amplitude. And now I use this program because I can add them both to the same series. So I'm going to add this to the bottom here. There it is. I could redo the analysis. I know what I'm going to get because the other program did it for me. But I would find that it's a square root power. And there is the answer. It's nice to be able to compare these two. I can see that they're both to the square root power, but they have a different constant. In other words, if I put 100 grams on this system, I'd get a period of about 0.4. If I put 100 grams on this system, I'd get a longer period with the different conditions. I could go this way as well. If I wanted a period of 0.6 for this system, I would need that value of mass. But for this system, I would need that value of mass. So here are those two math models simplified. And this is a really good way to transition to kind of the next step, which is, what determines this number. And what determines this number is it appears as though one or both of these things has an effect on period. In other words, my selection of these two constants changes this number. And the reason it changes this number is because one of them affects period, or both of them affect period. And so over the next couple school days, we're going to investigate the effect of each one to see if we can isolate those. But this was the effect of mass when we held the other two constant. So we want to know, how does the period change when I change the spring constant? But we're going to be good scientists and we're going to hold the other two variables constant. And then another experiment, how does the period change when the amplitude increases? And using good experimental procedure, we're going to hold the other two things constant. So those are really the next two things we'll investigate, because there is quite a bit of evidence from the data that something else or two other things are having an effect on the period. And so we want to isolate those variables in the next few experiments. Thank you.